In this lecture, randomization distributions, p-values, and statistical significance are introduced. Randomization distributions are similar to bootstrap distributions because they both utilize simulation, but use different assumptions to simulate sampling distributions, and they will be our means to calculate p-values and determine statistical significance. After this lecture, you should understand what a randomization distribution is and how to generate one, be able to calculate and interpret p-values from a randomization distribution, and determine the strength and significance of a p-value. A colonoscopy is a screening test for colon cancer, recommended as a routine test for adults over age 45, where the physician, a gastroenterologist, inserts a flexible fiber optic instrument called a colonoscope into the rectum and advances it through the colon, which is also called the large bowel. This is shown in the upper left illustration. A colonoscopy is used to diagnose colon and rectum problems and to perform biopsies and remove colon polyps, a small clump of cells that form on the lining of the colon that are typically not cancerous. The proportion of people with colon polyps expected to die from colon cancer is 0.01. The illustration in the bottom left shows the front of the colonoscope. In this illustration, you can see that the front of the colonoscope contains a light, a source of water, and an instrument channel where the gastroenterologist can insert a variety of tools, such as this wire loop to remove a polyp for a biopsy. One study provides evidence that colonoscopies may save lives. In this study, a sample of 2,602 people who had polyps removed during a colonoscopy were followed for 20 years, and 12 of them died from colon cancer. We want to test whether the proportion of all patients who died from colon cancer after having colon polyps removed in a colonoscopy is less than 0.01. We begin by writing the null and the alternative hypotheses. We are dealing with a single categorical variable. Did the patient who had a colon polyp removed during a colonoscopy die of colon cancer? Yes or no? Because we have a single categorical variable, we know that the parameter is p, the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer. We want to test whether this parameter is less than 0.01. We write the null hypothesis as p is equal to 0.01 and the alternative hypothesis as p is less than 0.01. In words, the null hypothesis states that the proportion of all patients who had a colon polyp removed during a colonoscopy and died of colon cancer is 0.01, and the alternative hypothesis states that the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer is less than 0.01. To calculate the sample proportion of patients who had a colon polyp removed during a colonoscopy but died of colon cancer, we take the number that died, 12, and divide it by the sample size, 2,602, and arrive at a proportion of 0.0046. Notice that our sample proportion is not equal to 0.01. Why? There are two possible causes. First, colonoscopies do in fact save lives by removing precancerous colon polyps, so the proportion that died of colon cancer after having these procedures is less than 0.01. Second, colonoscopies do not save lives, and just by random chance, our sample proportion is not 0.01. How can we rule out random chance, or at least quantify it? Recall that a bootstrap distribution is used to understand how sample statistics vary randomly from sample to sample. We used a bootstrap distribution to simulate the sampling distribution and estimate the standard error. It would be great if we could apply this logic to estimate how much a statistic varies from sample to sample if the null hypothesis is true. This is what a randomization distribution enables us to do. So how do we create a randomization distribution? Well, first, we need to simulate at least 10,000 samples, assuming that the null hypothesis is true. Second, for each sample, we need to calculate the statistic of interest. In this case, it is the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer. This would be the randomization sample proportion. We then save these statistics to create a randomization distribution. A sampling distribution is centered at the population parameter. In the case of a randomization distribution, the population parameter is the null hypothesis value. Now we have a way to estimate how much a statistic varies from sample to sample if the null hypothesis is true. How do we create a randomization distribution? Imagine you have 100 marbles. 99 of those marbles are white, and 1 marble is black. Let the white marbles represent patients who had a colon polyp removed during a colonoscopy, but did not die from colon cancer. And the black marbles represent the patients who had a colon polyp removed during a colonoscopy, but died of colon cancer. The proportion of black marbles you have is 1 over 100, or 0.01. This proportion is equal to the proportion of all patients we would expect that had a colon polyp removed during a colonoscopy, but died of colon cancer if the null hypothesis were true. Next, you place these 100 marbles into a bag. You mix it well and carefully pull out 1 marble. Record whether the marble is black or not, place it back into the bag, mix the marbles around, and repeat this process a total of 2,602 times. This is one randomization sample. Then you calculate the proportion of black marbles in this sample. This is your randomization sample proportion. Record this proportion in the randomization distribution and repeat this process 10,000 times. Now you've simulated a randomization distribution. Clearly this isn't practical, and a more efficient way to create a randomization distribution is with StatKey. This slide summarizes how to create a randomization for this example using StatKey. I will show you how through a demonstration. To do this in StatKey, we will select Test for Single Proportion under Randomization Hypothesis Test. Next, edit the data. Set count to 12. The number that died, and the sample size to 2,602. Click OK. Next, set the null hypothesis value to 0.01. Hit OK. Finally, generate 10,000 samples. There are several things to notice here. The randomization distribution is bell-shaped and centered at the null hypothesis value, which is 0.01. Our sample proportion 0.0046 is in the tail on the left side of the randomization distribution. Because it is so far off into a tail, it would be very unlikely to observe this sample proportion if the population proportion was in fact 0.01. So exactly how unlikely is it to observe a sample proportion 0.0046, or a sample proportion that is even more extreme than that? This is what is known as the p-value. The p-value is the probability of observing a statistic as extreme or more than what was observed if the null hypothesis is true. In this context, it means the probability of observing a sample proportion of patients who had a colon polyp removed during a colonoscopy that died of colon cancer of 0.0046 if the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer is 0.01. It is a mouthful. To find the p-value in StatKey, we need to know two things. First, we need to know the sample proportion, which is 0.0046. Second, we need to know the alternative hypothesis. Recall that the alternative hypothesis stated that the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer is less than 0.01. Because we're using the less than sign, we're interested in values less than our sample statistic, and thus are doing what we will call a left tail test. So we click the left tail box, and we change the bottom number to 0.0046. We hit OK. And we arrive at a p-value of 0.0018. Let's recap. The p-value is the probability of observing a statistic as extreme or more than what was observed if the null hypothesis is true. A p-value can be calculated from a randomization distribution by calculating the proportion of the randomization statistics as extreme or more than the observed statistic. In our case, the p-value was found to be 0.0018, which means that 1.8% of all randomization sample statistics, or 18 randomization statistics, were as extreme or more than 0.0046. We can interpret the p-value as follows. Given that the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer is 0.01, the probability of observing a sample proportion as extreme or more than 0.0046 is 0.0018. 0.0018 is a very low probability. That means it's extremely unlikely to observe these results if the null hypothesis were true. What exactly is the role of the alternative hypothesis? Was it used to create the randomization distribution? Nope. Only the null hypothesis was used. Was it used to calculate the p-value? Yes, the alternative hypothesis determines what we mean by as extreme or more and tells us which tails to use to calculate the p-value. When the alternative hypothesis contains a less than sign, this is called a left-tailed test. For a randomization distribution, we calculate the p-value as the proportion of randomization statistics less than or equal to the observed statistic. When the alternative hypothesis contains a greater than sign, this is called a right-tailed test. For a randomization distribution, we calculate the p-value as the proportion of randomization statistics greater than or equal to the observed statistic. Finally, when the alternative hypothesis contains a not equal to sign, this is called a two-tailed test. For a randomization distribution, we locate the observed statistic and calculate the proportion of randomization statistics in the smaller tail. The p-value is then calculated by doubling this proportion. This is the randomization distribution for the colon cancer screening example that I obtained before this recording. The alternative hypothesis was that the proportion of all patients who had a colon polyp removed during a colonoscopy that died of colon cancer is less than 0.01. We found the sample proportion, 0.0046, on the randomization distribution and calculate the proportion equal to or less than 0.0046. This p-value is 0.0020, and in our simulation we found it to be 0.0018, which is approximately equal. This is the same randomization distribution that I just showed you. The only difference is that the alternative hypothesis contains a greater than sign. We find the sample proportion, 0.0046, on the randomization distribution, and calculate the proportion equal to or greater than 0.0046. This p-value is 0.999. Adding this p-value and the one from the previous slide together will give 1.0 within rounding. Finally, we calculate the p-value when the alternative hypothesis contains a not equal to sign. We find the sample proportion, 0.0046, on the randomization tail, and notice that the left tail is substantially smaller than the right tail. To find the p-value, we double the proportion of randomization statistics less than or equal to 0.0046. This p-value is 0.0040. Now that we know how to calculate a p-value, we can begin to understand what statistical significance means. Statistical significance is a measure of strength against the null hypothesis and in support of the alternative hypothesis. When the p-value is very small, we say the results are statistically significant. Recall that a p-value tells us the likelihood of observing results as extreme or more than what we observed if the null hypothesis is true. A small p-value means it's very unlikely to observe these results. How small does a p-value need to be statistically significant? Prior to the start of an analysis, we must specify the significance level. The significance level is known as alpha, and if our p-value is less than alpha, we conclude our results are statistically significant. Alpha could be set to any value, but typically we set it to 0.05, 0.01, or 0.001. Traditionally, when people perform statistical analyses, they make formal statistical decisions based on the p-value. If the p-value is less than alpha, then one rejects the null hypothesis, concludes the results are statistically significant, and say that they have convincing evidence in favor of the alternative hypothesis. If the p-value is greater than or equal to alpha, then one does not reject the null hypothesis, concludes the results are not statistically significant, and that they don't have convincing evidence in support of the alternative hypothesis. Note that we never make a decision about the alternative hypothesis. We only ever reject or not reject the null hypothesis. A more nuanced and better use of p-values is to think of them as a measure of strength of evidence. When the p-value is very small, we have very strong evidence against the null hypothesis and in support of the alternative hypothesis. When the p-value is large, we have little evidence against the null hypothesis and in support of the alternative hypothesis. If the p-value is somewhere in between, we have some evidence against the null hypothesis and some in support of the alternative hypothesis. This is the way that I would encourage you to think about a p-value, rather than thinking about it as being used in a binary way. Either we reject or we don't reject the null hypothesis. Next time, we will discuss effect sizes. Knowing the size of an effect are essential for interpreting whether p-values are meaningful. Putting everything together we've learned so far, we arrive at formal hypothesis testing. Formal hypothesis testing involves stating a null and alternative hypothesis, setting the significance level, alpha, calculating the sample statistic of interest, calculating a p-value with a randomization distribution, and interpreting that p-value, making a decision about the null hypothesis, and writing a conclusion of the test in the context of the research question. Going back to the screening for colon cancer example, we calculated a p-value of 0.0046. This is very strong evidence against the null hypothesis and in favor of the alternative hypothesis. If we want to make a formal decision and alpha was set to 0.05, the p-value is less than alpha, so we would reject the null hypothesis and conclude our results are statistically significant. Relating these findings back to the original research question, is the proportion of all patients who died from colon cancer after having colon polyps removed in a colonoscopy less than 0.01? The answer is yes, because our p-value is extremely small.